Okay, so there's a few things I want to cover in this video. So let's start with rates of change. So let's say that we have dy over dx, and let's say that we also have dz over dy. Don't worry about the meaning of this new letter z here. It's just a new letter. It works the exact same way as x and y. And let's say that we want to find the value of dz over dx. Well, we can figure this out because dz over dx is equal to dz over dy multiplied by dy over dx. And you can think about this like fractions, with this dy here cancelling out with this dy here, so we're just left with dz over dx. Just really quick as well, if we had the exact same situation where we wanted to find dz over dx and we had dy over dx, but rather than having dz over dy, we had it the other way around. We have dy over dz. So in order to find dz over dx, we still want to use this formula here, but we need dz over dy where we have it in the flipped form here. Well, likewise, we can find dz over dy because it's equal to 1 divided by dy over dz. And again, you can think about this like fractions, because remember, when you do 1 divided by a fraction, it flips over this fraction here, so it's now going to be dz over dy like this here. We've also talked about this formula here in the chain rule video with respect to dy over dx and dx over dy. So here's just an example question to plug some numbers in to see how it works. So if dv over dr is equal to this here and dr over dt is equal to 4, find dv over dt. So dv over dt is going to be equal to dv over dr multiplied by dr over dt, and hopefully you can see this because these dr's will cancel out here to leave us with dv over dt. So therefore, if we plug the values into here, dv over dr is equal to the 16r squared minus 20, and dr over dt is equal to 4. So dv over dt is equal to these two multiplied together, so it's equal to 64r squared minus 80. I just also want to quickly define what the term differential equation is, because this phrase gets thrown around a lot and a lot of people think it's something like really complicated. A differential equation is just something with a derivative in it. So dy over dx, dv over dr, or dr over dt. If an equation has one of these in it, it's a differential equation. That's all it means when we say the phrase differential equation. Okay, so hopefully that's all fine. However, what's particularly difficult about the questions to do with this section is the way the questions are worded. A lot of people really struggle with this, and it makes the questions really difficult. A lot of people lose marks. The best way to understand them, in my opinion, is to go through as many questions as possible, which we'll do in this video, and we'll go through them slowly. I just want to first start with some notes. Firstly, the questions almost always revolved around volume or area, and you need to give these terms letters to use in your equations. Now, sometimes they'll just give you the letters, but other times you may actually have to assign these yourself. You can really assign them whatever you want, but commonly volume is given with a capital V, radius is given with a little r, and area is given with a capital A. These are the three most common, but I've also seen height with a small h, circumference with a big C, and population with a capital P. Again, the letters you use don't matter unless they specifically in the question say which ones they want you to use, which is quite often the case, but in other cases you can just use whatever letters you want if they're not assigned to you. Now, the hard bit that people find with these questions, including myself when I was at A level, is using the information that they give you in the question to make the differential equations yourself. And a reminder that a differential equation is anything with a derivative in it. Now, I'll go through loads of examples of this, but there's a very common pattern. They always use the word rate, and this is a really important word. Whenever you see the word rate, you need to be thinking d something over dt, where t is time, and this thing on the top here is whatever they're talking about in regards to rate. So for example, let's say that a question says the area is increasing at a rate of 5 centimeters squared to the second minus 1. Now we have this key word here, rate, so this is telling us it's going to be d something over dt. And as this particular part of the question is talking about area, it says the area is increasing at a rate. Therefore, this thing on the top is going to be area, which we denote with a capital A. So therefore, this particular part of the question is talking about dA over dt. And we're told the area is increasing at a rate of 5, and you can always just ignore the units here. And as it's increasing at a rate of 5, therefore dA over dt is going to be equal to 5. And that is the bit of information that you need to extract from this part of the question here. So here's another example. Let's say that says that volume is increasing at a rate of 8 centimeters cubed to the second minus 1. Again, we have this rate here, so it's going to be d something over dt, and the question's talking about volume, that's the rate that they're talking about. So we denote volume with a capital V, so it's going to be dV over dt, and the rate is told we're increasing at a rate of 8. We can ignore these units here, so dV over dt is equal to 8. If we're told that the radius is decreasing at a rate of 1 centimeter to the second minus 1, again we're told this crucial word rate, so it's going to be d something over dt, and we're talking about radius, so it's going to be dr over dt. We denote radius with a little r. This time it says that the rate is decreasing. Again, we can ignore these units here. So we're told that it's decreasing at a rate of 1. So dr over dt is going to be equal to 1. But as it's decreasing this time, it's going to be minus 1 because it's going down. With all the other ones, it's increasing. So it's a positive number as the rate is going up. But the rate is decreasing. So it's going to be minus 1 in this case. I just want to make one other note on something that comes up a lot. Let's say that the question is on the area of a circle. From this information alone, we can make a differential equation because we know that the equation for the area of a circle is pi r squared. A is equal to pi r squared, and we can differentiate this here in order to make a differential equation, dA over dr. So we can differentiate in terms of r. So if we differentiate this here, this pi coefficient is going to come down like this, and if we differentiate r squared, it's going to be 2r. So dA over dr is equal to 2 pi r, and this is a differential equation that we can use in our answer. Another example is if they say in the question that they're talking about the volume of a sphere. Well, we know that the equation for the volume of a sphere is V is equal to 4 over 3 pi r cubed. So therefore we can find a differential equation by differentiating this here. So it's going to be dV over dr is equal to 4 over 3 pi, and then this is multiplied by r cubed differentiated, which is going to be 3r squared, and then this 3 denominator is going to cancel out with this here. So we're left with dV over dr is equal to 4 pi r squared, and this we can use in our answer. Okay, so here's an example of a past paper question where we're told that the area of a circle is increasing at a constant rate of 1.5 centimeters squared per second, and we need to find to three significant figures the rate at which the radius of the circle is increasing when the area of the circle is 2 centimeters squared. Now, this can seem pretty daunting because there's a lot of words in this question, so let's try and break it down. So firstly, let's try and find what the question actually wants us to find, what it actually wants as the answer. And it says that it wants us to find the rate at which the radius of the circle is increasing. So we have this key word here, rate, so it's going to be d something over dt, and we're told it's the rate at which the radius of the circle is increasing, with radius denoted with this r here. So therefore this r here is going to be on top. So we need to find dr over dt. Okay, so let's look at some other parts of the question. So for the first sentence, it says that the area of a circle is increasing at a constant rate. Now again, we have this rate here, so it's going to be d something over dt, and we're told that the area A of a circle is increasing at a constant rate. So this A here is going to be on top like this here, and we're told that the area is increasing at a constant rate of 1.5. Again, you can ignore these units here. So as it's increasing at a constant rate of 1.5, dA over dt is going to be equal to this 1.5 here. And we can also get another differential equation out of this because we're told that it's the area of a circle, and like we talked about before, this is enough to give us enough information about to find a differential equation, because we know that the area of a circle is pi r squared, and therefore we can differentiate this to get dA over dr. So if we differentiate this in terms of r, it's going to be this pi multiplied by, and if you differentiate r squared, it's going to be 2r. So this is going to be equal to 2 pi r. So we have now got a differential equation for dA over dr. So when we look at what we want for the final answer, we want dr over dt. And when we look at the two differential equations that we're going to multiply together, what we're going to want is, okay, so we're going to want dr in the numerator here, because that's what we want to be left over with. And in the other differential equation, in the denominator, we're going to want this dt here, because we want this left over in the final answer. And then we're going to want the same thing here and here, so they cancel out in the end, just leave us with dr over dt. And when we look at the two differential equations that we have, common in both of them, we have this a here. So therefore we're going to have dA here and dA here, and then these two are going to cancel out to just leave us with dr over dt, like what we want. Okay, so we need dA over dt, which is what we've got here, is equal to 1.5, and we need dr over dA. But at the moment we've got this we've got it flipped over. We've got dA over dr, and we talked about this at the start of the video, how to deal with this. dr over dA, which is what we want, is equal to 1 divided by dA over dr, with kind of like this fraction flipping like this here. So therefore we just sub in what we have for dA over dr here, so it's going to be 1 divided by 2 pi r is equal to dr over dA, which can be written as 1 over 2 pi r. So now we have the equation for dr over dA and dA over dt, so we can sub these in like this here, and then we can move this 1.5 into the numerator. So we've got dr over dt is equal to 1.5 over 2 pi r. Now when we look at the question, what it wants us to find, it wants us to find the rate at which the radius of the circle is increasing when the area of the circle is 2 centimeters cubed. So we need to find dr over dt when the area of the circle is equal to 2. Now this differential equation here is not in terms of a, it's in terms of r, but this isn't a problem because of course we know that the area of a circle is this here, so we can just sub in a as 2 and then rearrange in order to make r the subject and then sub it into here. So just sub a as 2, which is what I've done here, and then move this pi onto the other side, divide both sides by pi, so it's 2 over pi is equal to r squared. So then r is equal to 2 over pi square rooted like this here. So this is r when the area of the circle is 2 centimeters squared. So therefore if we sub this in as r, we get dr over dt is equal to 1.5 over 2 pi, the square root of 2 over pi, and it wants it to 3 significant figures. So if you put this into your calculator to 3 significant figures, this is 0.299. So here's another example of a past paper question where we're told about figure 2, which is this here, which is a cylindrical rod which is expanding as it's heated, and we're told that the radius of the rod is x and the length of the rod is 5x, and we're told that the cross-sectional area, so the cross-sectional area is going to be this circle face here. This is the cross-sectional area. We're told that it's increasing at a constant rate of 0.032 centimeters squared per second, and we need to find dx over dt when the radius of the rod is 2 centimeters. Okay, well we're told that the radius of the rod is x, so therefore when it says find dx over dt when the radius of the rod is 2 centimeters, what it's saying is find dx over dt when x, because that's the radius, is equal to 2. Okay, so we need to find dx over dt, and we can make some differential equations using the information that we have here. Firstly, we're told that the cross-sectional area of the rod is increasing at a constant rate, so we have this keyword here, rate, again, so it's going to be d something over dt, and we're told that the cross-sectional area of the rod is increasing at a constant rate. So the thing that's on top of the differential equation is this cross-sectional area here, and let's call this A, so this is going to be the area of this circle here, so it's going to be dA over dt, and we're told that it's increasing at a constant rate of 0.032, so dA over dt is equal to 0.032. Okay, so we can get some more information from this, because this cross-sectional area here, so the area of this circle here, well, we know that the area of a circle is equal to pi r squared, so therefore the area of this cross-sectional area here, bearing in mind that A is the cross-sectional area, so A is going to be the area, is going to be equal to, so if we sub in pi r squared, it's going to be pi x squared, because we're told that the radius of this rod here is x. So A, the cross-sectional area, is equal to pi x squared, where x is the radius, and then we can differentiate this, so dA over dx, if we differentiate this here, it's going to be pi multiplied by, and then if you differentiate x squared, it's going to be 2x, so dA over dx is equal to 2 pi x. So when we look at what we need, which is this dx over dt here, so when we look at the two differential equations that we're going to want to multiply together, okay, well, in the numerator of 1, we're going to want dx, because we want this at the end in the numerator, and then in the other differential equation we want this dt in the denominator here, because again we want to end up with this here. And if we look at the two differential equations that we've got, dA over dt and dA over dx, what is common in both of them is this a here, so we're going to do the other two terms as dA like this here, so they will both cancel out at the end to just leave us with dx over dt like this here. Okay, so we have dA over dt, this is this 0.032, but we don't have dx over dA, we have dA over dx, so we're going to have to do the thing we did before, where dx over dA is equal to 1 divided by dA over dx, so therefore if we sub in the value for dA over dx, which is 2 pi x, it's going to be 1 divided by 2 pi x, which is going to be 1 over 2 pi x. So dx over dA is equal to this here. So therefore, if we sub the values in for dx over dt, it's going to be dx over dA, which is just 1 over 2 pi x, multiplied by dA over dt, which is 0.032. So this will go in the numerator like this. So dx over dt is equal to 0.032 over 2 pi x, and we need to find dx over dt when x is equal to 2. So we just sub 2 into this here, so dx over dt is equal to 0.032 over 2 pi 2, and if you put this into a calculator to three significant figures, it's 0.00255. And then for part B, we need to find the rate of increase of the volume of the rod when x is equal to 2. So let's try and figure out what this question actually wants us to find. So it wants us to find the rate, so it's going to be d something over dt. It wants us to find the rate of increase of the volume. So if we call volume V, therefore is going to be dV over dt, and this is what we're looking for here. Now we haven't actually encountered volume yet in this question, so we're going to have to find a new differential equation that is linked to volume in some way, and we can do this because this is just a cylinder, this rod here, and you need to know, by the way, for your exams, kind of the volume of basic 3D shapes, and you need to know that the volume of a cylinder is pi r squared L. So that's the volume of the cylinder, and therefore we can just plug the values of x into this here. So V, the volume, is going to be equal to pi r squared, and we've already talked about that the radius is x here, multiplied by L, and we're told that the length of the rod is 5x. So V is equal to this here, and we can simplify this, bring the 5 to the front, and then x squared multiplied by x is going to be x to the power of 3. So V is equal to 5 pi x to the power of 3, and then we can differentiate this. So it's dV over dx, and then we can differentiate this in terms of x. So it's going to be 5 pi multiplied by, and then x to the power of 3 differentiated is 3x squared, and then 5 times 3 here is going to be 15. So dV over dx is equal to 15 pi x squared. So when we look at what we want for the final answer, we want dV over dt. So when we consider the differential equations that we want to multiply together, okay, well, we're going to want to have a dV in the numerator for one of the differential equations because we want this left over at the end, and then in the other differential equation we're going to want a dt in the denominator because we want to be left over with this. So therefore we want two of the same term here that are going to cancel out to just leave us with dV over dt. And if we consider the previous previous differential equations that we've got. So at the moment we've got dv over dx, and we also had a differential equation for dx over dt from part A. So therefore what we can do is we can write dx and dx like this here, and then write out, multiply together the dv over dx and dx over dt differential equations, and then these dx will cancel out in order to give us dv over dt like this here. So therefore dv over dt is going to be dv over dx, so we sub in this 15 pi x squared multiplied by dx over dt, so we just sub in this here, and then we can simplify this because this pi will cancel out with this pi, and then this x will cancel out with one of these x's here, and then this 15 will multiply this 0.032, so we're left with dv over dt is equal to 0.48x over 2 like this here, and we need to find the rate of increase of the volume of the rod when x is equal to 2. So we need to find dv over dt when x is equal to 2, so just sub in x is 2 like we have here, and then these 2's here will just cancel out to leave us with dv over dt is equal to 0.48. So here's one more exam question that I want to go through quickly, because this one's a bit different and I think this one's quite common to come up, something like this. So we're told that liquid is poured into a container at a constant rate of 30 centimeters cubed per second, and also liquid is leaking from the container at a rate of 2 over 15 V centimeters cubed per second, where V is the volume of liquid in the container at a particular time, and we need to show that this equation here is true. So for a question like this, I think the best thing to do is to draw a diagram so you completely understand and kind of envision what's going on. So in the first sentence, we're told that liquid is poured into the container at a constant rate of 30 centimeters cubed per second. So liquid is poured into the container at a constant rate of 30. Okay, and then in the second sentence we're told that liquid is leaking from the container at a rate of 2 over 15 V centimeters cubed per second. So liquid is leaking from the container at a rate of 2 over 15 V centimeters cubed per second like this here. So we need to consider what differential equation is going on, and you can see that for both of these they're both rates, so it's going to be d something over dt, and both of these are going to be affecting this v here, the volume of liquid in the container at a particular point. Liquid is being poured into the container, so that's going to increase the volume of liquid in the container, and liquid is leaking from the container, so that's going to decrease the volume of liquid in the container. So this rate here is going to be increasing the volume, but this rate here is going to be decreasing the volume. So as it's the volume, it's going to be dv over dt. Another clue that it's the volume that these are affecting is when you look at the rates, they're written in terms of centimeters cubed, and remember that centimeters cubed is volume. If it was centimeters squared, for example, this would be area, but as it's centimeters cubed, this is volume here. So when we're writing a differential equation for dv over dt, we need to consider both of these factors because they're both simultaneously affecting the volume. So therefore dv over dt is going to be 30, so that's the liquid being poured into the container, and that's positive because liquid is being poured into the container, so the volume's increasing. And then it's going to be minus 2 over 15v down here. This is minus because it's leaking from the container, so it's decreasing the volume. And this is dv over dt. It's 30 minus 2 over 15v. We need to write both of these in the same equation as they're both affecting each other directly at the same time. So this is dv over dt, and then we need to show that this equation here is true. So we just need to rearrange this. We have this minus 15 in front of the dv over dt on this side. So if we multiply everything by minus 15, we get minus 15 dv over dt is equal to 2v minus 450, which is of the form that we need here. So if you have a question like this and you're unsure, draw a diagram like this here in order to help understand what's going on, so you can write an equation like this here with the positive and negative rates all in one. Now, along these lines, they sometimes like to ask more general questions that don't even have numbers in them, like this one here. So just be aware of these, as these can be quite tricky if you haven't seen a question like this before. The new specification seems to especially like these, I've found. So we're told that a population is growing at a rate which is proportional to the size of the population, and we need to write a general differential equation that models this process. Now, this is actually question 5 in the book in exercise 9J. I normally don't like taking questions from the book, but this is kind of a pretty standard question that they could ask, and also population growth is referenced in the specification, so I wanted to cover it. So we're told that population is growing at a rate, so remember this is the key word, that rate means it's d something over dt, and we're told that population is growing at a rate. So if we call population p, dp over dt is growing at a rate, so it's dp over dt, which is dp over dt, which is what we're trying to find. And we're told it's proportional to the size of the population. Now, hopefully you know what proportional means. We talked about proportionality back in year 1 chapter 5 in the modelling video, so go back to that if you need a reminder. But when we say something is proportional to something, we use this alpha symbol like this here. So it's proportional to the size of the population. The size of the population is just p. P represents the size of the population. So dp over dt is proportional to the size of the population, which is p, like this here. And we need to write this as an equation, and when you write something as proportional to something, you can replace this kind of with a k, like this here, and an equal sign. So we can write that dp over dt is equal to kp, where k is some sort of constant. We don't need to like find what k is, because we're not given any information about any values. We just say that k is a constant and dp over dt is equal to kp, and that's the final answer. So here's another example where we're told that the rate of decrease of the concentration of a drug in the bloodstream is proportional to the concentration of the drug which is present at the time, and we need to show that this can be modelled by this differential equation like this here. So we're told it's a rate, so it's going to be d something over dt, and we're told it's the rate of the concentration of a drug in the bloodstream, and we're told that we should label this concentration capital C. It's going to be dc over dt like this here, and we're told this is proportional, so it's proportional to the concentration C of the drug which is present at the time, so therefore this is proportional to C, like this here. However, we're told that it's a rate of decrease, so therefore it's going to have a negative sign in front of it like this here. It's a rate of decrease, and therefore we need to show this can be modelled by this differential equation here. So we just replace this alpha sign with an equal sign and a k, where k is a constant. Now k has to be a positive constant because we need this to be a rate of decrease, and if k was a negative number, say like -1 for example, if this was -1, this would cancel out with this minus number and then just leave it equal to c, so therefore it would be a positive rate now. So it has to be a number that's bigger than 0, so it doesn't cancel out the negative sign because it's a rate of decrease. So here's another example where we're told that the rate of decrease of the radius of a mint is inversely proportional to the square of the radius, and we need to write a differential equation modelling this process. So it's a rate, so it's d something over dt, and we're told that it's the rate of decrease of the radius of a mint. So if we say it's the radius, so it's r, and we call it little r, like this here. So we're told it's inversely proportional, so it's proportional like this here. Is inversely proportional to the square of the radius. So the square of the radius is going to be r squared, but we're told it's inversely proportional, so it's going to be 1 over r squared, as that's what inversely proportional means. It means 1 over whatever it says it's proportional to. But it's also a rate of decrease, so therefore there's going to be a minus sign at the front here. So therefore dr over dt is proportional to minus 1 over r squared. It's the rate of decrease that's inversely proportional to the square of the radius. And to write this as an equation, we just replace the proportional alpha sign with an equals and a k like this, so the k goes in the numerator like this here. So dr over dt is equal to minus k over r squared. So here's another example of an exam question where we're told that liquid is pouring into a container at a constant rate of 20 centimeters cubed per second and is leaking out at a rate proportional to the volume of liquid that's already in the container, and we need to show that this satisfies this differential equation here. So again, we have rate, so it's the classic d something over dt, and this is the same as the question before where liquid is coming into the container and it's also leaking out, so it's going to be affecting the volume of liquid that's in the container. So it's going to be volume, so it's going to be dv over dt, what we're looking for. So like the question before, it'd be good to draw a diagram of the container to show what's going on. So it says that liquid is pouring into a container at a constant rate of 20 centimeters cubed per second. So liquid is pouring into the container at a constant rate of 20 and is leaking out at a rate that is proportional to the volume of liquid that's already in the container. So it's leaking out at a rate that is proportional to the volume of liquid that's already in the container. So the volume of liquid that's in the container, as we've talked about, is V. So it's proportional to V, and remember, when you say proportional to V, you can also write that as K V, where K is a constant. So therefore dV over dt can be written as, so the increasing rate is the 20 here, so that's going to be positive, and then the decreasing rate, which is the leaking out of the liquid at the bottom, is going to be this kV here, so it's going to be minus kV. So dV over dt is equal to 20 minus kV. So here's one final question for this video. So we're told that liquid is pouring into a cylinder container at a constant rate of 1,600 centimeters cubed per second and is leaking out at a rate that is proportional to the square root of the height of the liquid that's already in the cylinder. We're also told that the area of the circular cross section of the cylinder is 4,000 centimeters squared, and we'll get on to a moment of why that's relevant. And we need to show that dH over dt can be written in this format here. Okay, so again, it's talking about rates, so it's going to be d something over dt, and this is the same question that we've already seen, very similar to this, where it's liquids into a container, and we're talking about the volume of the liquids in the container, so it's going to be V. Okay, so let's look at the numbers. So we're told that liquid is pouring into a large cylinder at a constant rate of 1,600. So if we draw a diagram in order to help understand this, so liquid is pouring in at a constant rate of 1,600 and is leaking out at a rate proportional to the square root of the height of the liquid already in the cylinder. So it's pouring out at a rate that is proportional, so this proportional symbol here, to the square root of the height of the liquid that's already in the cylinder. And we're told in this question that the height of liquid in the cylinder can be represented as h here, so it's proportional to the square root of this h value here, so the square root of h. Remember, when it's proportional to, we can rewrite this in terms of a constant. We normally do it in terms of k. For the sake of this question, for explaining it, I'm going to use a different letter, and you'll see why in a sec. So I'm just going to use a, for example. So a root h like this here. So liquid is pouring out or leaking out at a rate of a root h like this here. So dv over dt is equal to the positive rate 1,600 here minus the liquid that's the rate of liquid that's leaving, which is a root h. So we have dv over dt, but the problem is this isn't what we need for our final answer. We need dh over dt. So what we're going to have to do, we're going to have to do the things that we've done before, where we multiply two differential equations together in order to give dh over dt. So what we're going to have to do, we're going to have to find another differential equation. So how do we do this? Well, let's look at the question. So the question is based around a cylinder container that is containing liquid, and we're told that the area of the circular cross section of the cylinder is 4,000 centimeters squared. So it's a cylinder container that the liquid is held in, like this here, and this blue section here is the liquid that's in the cylinder, and it's got a volume of V. So we know that the circular cross section of the cylinder is 4,000, so this is this cross section up here, and it's also this cross section down here. So this is 4,000. And we're also told that the height of the liquid in the cylinder is represented by h. So the height of the liquid in the cylinder is represented by h here. And you can kind of see that V is actually this blue cylinder here is actually a cylinder. It's just inside the bigger cylinder, which is the cylinder container, the whole cylinder container. But the volume of liquid makes its own container, with this cross section here being 4,000 here, and the height of the cylinder, or the length of the cylinder, being h, like this here, which makes up the volume. So therefore we have an equation for the volume of the liquid here. It's going to be 4,000, the cross-sectional area here, multiplied by h, which is the length of this blue cylinder here. So we have this equation here, and we can form a differential equation using this here, because we can differentiate this, so it becomes dv over dh, which is now going to be, so this h is going to go away, so it's just going to be 4,000, like this here. And now we have two differential equations that we can use in order to find dh over dt. So dh over dt is going to be, so we're going to want dh up here and dt down here, like this. And as we've got v common in both of the differential equations, we're going to put dv here and dv here, so these two will cancel out to just give the dh over dt. Okay, we have the dv over dt here. This is this 1,600 minus a square root of h. We don't have dh over dv, we have dv over dh. So what we're going to have to do to find dh over dv is do 1 divided by dv over dh, which is going to be 1 divided by 4,000, which is going to be 1 over 4,000, like this here. So we've flipped the fraction to dh over dv. So therefore, if we sub in the values, dh over dt is going to be equal to dh over dv, which we figured out as 1 over 4,000, multiplied by dv over dt, which is this 1,600 minus a root h. So we have this equation here for dh over dt, and we can expand this bracket here. So we're going to do 1,600 divided by 4,000, which is going to be 0.4, and then this is minus the a over 4,000 root h, like this here. And we can make a substitution, so this now becomes dh over dt is equal to 0.4 minus kh, which is what's required here, where k is equal to a over 4,000. So for part B, we're told that when h is equal to 25, water is leaking out of the hole at 400 centimeters cubed per second, and we need to show that k is equal to 0.02, and k is this constant that we figured out as part of our answer of the differential equation in part A. Now, when I first read this, I misread it and misunderstood what it was saying. So when it says water is leaking out of the hole at 400 centimeters cubed per second, the way that I first interpreted that is there's an overall volume of water in the container, and I thought that was saying that overall it is going down by a rate of 400 centimeters cubed per second, but that's not what it's saying. What it's saying is that water is leaking out of the hole at 400 centimeters cubed per second. So it has nothing to do with the rate up here, and it has nothing to do with the overall rate of the volume of water going up or down. It's only concerned with the rate of the water leaking out of the hole down here, which is at a rate of 400. So this volume of water could be going up or it could be going down. It doesn't matter for this question. All we know is that water is leaking out of the hole down here at a rate of 400. And actually, if you think about it, as the water is coming in at a constant rate of 1,600, and in this example it's leaving at a rate of 400, the overall volume of water is obviously going to go up, as this number is bigger than this number. So there's more water coming in than coming out of the hole at the bottom. But what this question is saying is that water is leaking out of the hole at the bottom here at 400, and we know that the rate is a root h, which we figured out in part A. So therefore we can say that 400 is equal to a root h, like this here, and we know that h is equal to 25, so therefore 400 is equal to a root 25, so 400 is equal to 5a, and divide both sides by 5, so 80 is equal to a. And we did the substitution in part A that k is equal to a over 4,000, so therefore k is going to be 80, because we subbed in 80 as a, 80 over 4,000, so k is equal to 0.02, which is what's required. I just want to end this video on one note. This video, kind of making these differential equations, is going to be very, very closely linked to integration in year 2, because these kind of differential equations, you can integrate them.